Hello, my name is Mohammad Zari, and in this session I'll be presenting a new method that we recently developed at University of Waterloo to estimate the monetary benefit of improving AADT accuracy in terms of network screening results. The structure of this presentation is as follows. First, a brief background will be provided for the concept of network screening and safety performance functions. Then, the proposed method for benefit estimation of improving AADT accuracy will be described. Finally, I'll go through a sample result from an implementation of the framework. Okay, so network screening is the first step in road safety management program that is presented in Highway Safety Manual or HSM. It is basically a process to prioritize different traffic sites such as intersections or roadway segments for more detailed safety evaluation that is performed in the next steps of road safety management program. There are several methods in HSM for network screening. Two more common methods are using empirical base and potential for safety improvement as risk estimates, which have been shown in different studies to provide better performance in comparing to others. SPF or Safety Performance Function is a predictive model that can estimate the frequency of crashes of certain type as a function of roadway geometry and operational characteristics. In the given example, black solid line can represent a fitted SPF to our data points. Since crashes are random and rare events, it is recommended to use estimated long-term crash rate instead of observed crash rate as a more robust risk measure. The common method to estimate the long-term crash rate is called empirical base or EB method. After applying EB method, we can estimate PSI or potential for safety improvement for each site, which is basically defined as a difference between long-term crash rate, comes from EB method, and predicted crash rate, which comes from SPF. PSI is usually estimated in property damage only crash units, which we usually call it PDO units. And higher PSI basically means there is more potential to reduce crashes by implementing more safety audits or safety improvements. One of the most challenging inputs for network screening is AADT data, which often suffers from a considerable amount of error and uncertainty. Installing permanent count stations on every link in the network is usually impractical and cost prohibitive. As a result, several methods are used in practice to estimate AADT data based on site-specific short-term counts or data from nearby count stations and/or site characteristics. The AADT estimates from these methods are subjected to error because of incorrect grouping count stations, incorrect association of groups for the short-term count sites, and the random day-to-day variability in the traffic counts. In our paper, we proposed a framework to quantify the magnitude of the potential benefit associated with improving these AADT estimates in relation to network screening results. In order to quantify the impact of AADT error in terms of network screening result, we proposed a simulation method to estimate the monetary benefit of improving such data. The framework has four main modules that simulates noisy AADT data and compares its network screening results with the true benchmark based on actual data without any noise. In the first module, we simulate long-term crash rate and also PSI values based on SPFs and available AADT data and estimated dispersion parameter. We assume that these values are correct and true values, so we have the true PSI for each traffic location. We note that in reality, we don't have a perfect AADT data, which is data without measurement error, which is why we are using a simulation-based approach for the evaluation. In Module 2, we add some random error to our AADT data based on a given distribution and its parameters. The modified AADT is used in Module 3 to develop a new set of SPFs, determine new PSIs, and then a new top hotspots. These AADT data and the resulting network screening outcomes reflect the conditions that are usually experienced in practice because the AADT data that we have available in practice always contains some measurement errors. In Module 3, we develop new set of SPFs based on noisy AADT data from Module 2 and simulated crash counts from Module 1. Then PSI and corresponding ranks for each site is estimated using the new set of SPFs. Finally, in Module 4, we compare the total true PSI values from true hotspots, which is the network screening results using perfectly accurate ADT data, and hotspots based on the noisy ADT data. The difference in PSI can be converted into a monetary value based on the societal cost of each PSI unit. Here, a sample input and output of the framework for a real-world example is presented. The dataset includes crash and ADT data for intersections of 4 types located in London, Ontario, Canada. In the given plot, the x-axis represents the amount of error that has been introduced to the AADT data in terms of coefficient of variation, which is the standard deviation divided by mean. And the y-axis shows how much cost we're gonna lose given having that much error in our AADT data. We can use this graph to identify the monetary benefit of improving the accuracy of the AADT data. For instance, if we estimate that currently there is about 40% error in our AADT data, then reducing it to 20% will save us about $100,000. Thank you for watching this presentation.